Welcome everyone, and thank you for joining us for today's webinar. My name is Dan Abir, and I'll be hosting the webinar today. Our webinar's title is Software plus Hardware plus Automation equals CFD Acceleration, and will be presented by Greg Paget from Total Sim US. Getting the best results fastest is the holy grail of engineering, modeling, and simulation. In today's webinar, we will demonstrate how using the right combination of tools and processes can lead you to better results at a lower cost and allow you to accelerate innovation. We will touch on the following topics: software, in-house, open source, commercial, government, academic, hardware, GPUs, CPUs, workstations, HPCs, and cloud, automation tools, scripting, APIs, macros, templates, and custom development. We'll also include some collateral and links that you might find interesting in the chat section of the webinar and/or in an email following the event so that you can access it. One of them speaks about faster CFD using SimCenter, StarCCM Plus, and NVIDIA RTX GPUs on an HP Z8. And then another one is 3 reasons you should try Cloud HPC. Before we jump into the webinar, I wanted to do a little bit housekeeping. The webinar will be recorded and made available upon request it's available to everybody attending and upon request to people who have not attended. Your microphone and video will be muted during the presentation. If you have any questions during the webinar, please type them into the Q&A tab here so that we can address them after the presentations are completed. And you can also look for any updates and links and messages in the chat window here. Of course, don't forget to download and check out the collateral after the event. A bit about Total Sim: was founded in 2009, has a sister company currently in the UK. We're about 10 engineers with CFD, aerodynamics, and physical testing experience in a variety of industries, including aerospace, automotive, renewable energy, and more. We have 3 primary areas we can help quickly move you from concept to reality by leveraging our capabilities in engineering, prototyping, test services, and software. We can help you with the design analysis and optimization, improving, creating better designs, simulating, prototyping, and testing. So building, modeling, testing, and of course, correlating the results, and train and mentor you if you want to improve your CFD skills or to bring them in-house. We're also Siemens a reseller and partner, and able to help you bring the digital enterprise in-house if you have an interest there. Wanted to briefly review some of the critical issues impacting CFD acceleration and performance before we jump into more detailed discussion. Recent progress in CFD acceleration has been propelled by hardware like GPUs, software innovations such as native parallel solvers, and AI ML techniques that create efficient surrogates for full fidelity simulations. These enable not just speed, but also scalability for large-scale problems, such as full aircraft aerodynamics or urban wind flows. But they also create challenges for people and companies to make sense of this all and determine which are the right tools and combinations that would best suit your company size, use cases, and proficiency levels. As simulation fidelity increases, driven by demands for higher accuracy in complex real-world scenarios, the computational cost has skyrocketed, often taking weeks or months on traditional CPU-based systems. Acceleration efforts focus on reducing these timelines to hours or days through hardware advancement, algorithmic innovations, automation, and AI integration. In this webinar, we will discuss the trinity that will help you and your team make better informed decisions and accelerate your use of CFD and improve the performance and the results that you get. Which software is right for you? Which hardware? And should you conduct manual or automation or a combination of both of them? The best CFD solver choice depends on your specific needs, resources, and priorities. Open source solutions offer flexibility and cost savings, but might require greater in-house expertise. COTS software provides dedicated support and user friendliness, though with higher upfront costs. Government and academic efforts often drive innovation and address specialized needs, while in-house development offers ultimate control but comes with a significant resource commitment and risk. The trend towards open source and cloud-based CFD is democratizing access and making high-performance simulations more attainable for a wider range of users and industries. Optimizing CFD simulation solve times involves careful consideration of hardware components, particularly CPUs in the areas of core count, clock speed, cache, etc., and the potential for GPU acceleration. It's important to note that on GPU acceleration, it's not suitable for all CFD problems, and that is also being addressed and trying to increase the type of problems that it can help with. Understanding the concepts of strong and weak scaling helps evaluate the effectiveness of parallel processing and optimize hardware configurations for specific CFD workflows. Finally, CFD process automation leads to substantial savings in engineering workflows, allowing engineers to focus on higher level tasks and accelerate product development. Here's how automation achieves these time savings. Faster and more efficient iterations, automating steps like geometry creation, meshing, and setup. Anything that you can do on a recurring basis can be captured in a way that you're able to leverage that and free up some time that your experts can spend on analyzing the results or creating better designs. Reduced reliance on manual effort and error reduction. Once again, similar type of results so that you can troubleshoot problems earlier and have to spend less time doing rework. And of course, streamlined workflows that create some consistency regardless of the level of the user throughout the organization. In this webinar, we'll dig a bit deeper into some of these solutions and potential ways to map them to your type of problems or use cases. We hope to demonstrate the benefits of optimizing your CFD to create better, more complex results faster. With this, I would like to introduce you to our presenter to dig into some more details. Mr. Greg Padgett has been with Total Sim since 2011 when he graduated from The Ohio State University with a degree in aeronautical and astronautical engineering. As an aerospace engineer, Greg has experience with both CFD and aerodynamic design. Greg is, quote unquote, a jack of all trades, supporting projects from aerospace to automotive to industrial design and more. He also supports our customers using our custom open foam CFD and our Star CCM Plus customers. He has been working with simulations since 2011 and has been in several races series such as NASCAR, Daytona Prototype International, Le Mans Daytona Hybrid, GT3, and more, and has also supported wind tunnel and track testings through the years. In his spare time, Greg enjoys rock climbing and woodworking. Greg, you're welcome to begin.
Thanks, Dan. Let me get the presentation back up and we'll go through that. So what exactly is compute Dan's been talking about? And it can come in a lot of flavors. There are laptops, if it's your first kind of point of entry. They give you, something affordable to start with. They've got, low cost of entry, but they have the drawbacks with limited power, but they still have low maintenance costs. So it's kind of an easy thing to start with. The next kind of step up from that is something like a desktop workstation. They're still affordable. They've got more computing power to them. They've still got low maintenance costs, but you're still limited in what kind of models you can do, what kind of physics, how big it is. On a workstation or a laptop, you might be able to do 1 to 5 million cell models, but on a desktop, you can start getting some enterprise hardware in there and you can start getting up to things like 20, 30, 40 million cells with respectable turnaround times. Once you've kind of outgrown something like that, though, you get into that high performance computing servers, and those, start becoming a decent capital expense to build. You could be looking at, you know, $25,000 to $200,000 for a decent sized system, depending what you're putting in there. Uh, and that's where some people tend to go from desktop to cloud computing. And we have a partnership with Ohio Supercomputer here in town where some of our customers who aren't ITAR restricted or anything like that can move down there, bring their own license, and go straight from running on a desktop to suddenly having access to thousands of cores and GPU acceleration. For those, out on their own, they can also go to services like AWS, Azure, and Google for that kind of stuff. And there's a benefit there because you instantly have access to thousands of cores, a lot less maintenance requirements, uh, but you don't have any control of your hardware, and you still have to bring your own software. The next thing there is Siemens Star CCM Plus with its built-in SimCenter X. And that kind of gets into the software as a service aspect of it. You can launch something like Star CCM and within 1 or 2 clicks, automatically connect to an AWS server and pick a model size of maybe 75 cores up to I think 600 cores and start going immediately. And with this, because there's no AWS setup or Google setup, you don't have to go through and pick bucket sizes and what nodes you want to run on and a bunch of involvement. It's a couple clicks and you're up and running.
Recording in progress.
You can pick whichever software version you want, and it ties into Teamcenter if you've got people spread out across the country, around the world, to push and pull products around. But beyond just CPU, there's the GPU, which Dan was mentioning, and that is where a lot of speed up has come in the past 4 or 5 years, really. There's been hints of it coming back maybe a decade, 15 years or so, but with the advent of a lot of the AI systems leading these GPUs to have massive memory or RAM chips in them now, instead of the old, 1, 2, 3, 4 gigs in a video card. Now you have systems that have, like the H200, I think has 140 gigs in one video card. And you can start putting actual CFD models into that. And that gives you the benefit of massive speed ups. While CPU is the traditional, workhorse and supports basically all the physics because it's the, general processor that everything runs on, it still has the ability to go from 4-core laptop up to a giant HPC system with tens of thousands of cores. But that GPU accelerator then can take whatever mesh you've generated, and now you can go from thousands of cores or hundreds of cores to make your mesh if you choose, and go down to maybe 1 or 2 of these H100s. And the scaling on it is pretty wild because if you look at some of those numbers on those plots, those are solve times in minutes. And this comes from a previous webinar we did with heat transfer. We took a NASCAR Cup car and we were working on an exhaust system, and the steady state thermal models on a 192 core system were taking 10 to 15 hours to solve. We were able to then put those on GPU for those solves, and depending on what kind of physics you're looking at, whether it's constant density or ideal gas, I mean, you're getting anywhere from 7 to almost 30 times speed up to where now you can get a whole simulation back in an hour, hour and a half, and depending what you're doing, maybe even down to just 20 or 30 minutes. And the one thing to remember is the memory is king on all of these GPUs. If you end up buying a consumer grade card that only has 8 gigs of memory, if you've got a relatively small model and a couple million cells, you can still get massive speedups for that, and you can do that easily. But if you're doing something on the size of aerospace or automotive models with, low 100 million cell models and higher, you're going to look at something like an H100 or A100s, and you're going to potentially need a couple of them to see some of those benefits. But how do you choose which is right? And unfortunately, there's no one size fits all answer. building your own in-house system is great for people who can support their own infrastructure and they have the capital to go and spend on that. But once you've spent it, ideally the only thing you have to worry about is power and cooling and occasional hardware updates. And then that system could run for 10 plus years and keep working. Obviously you could do hardware updates and get more efficient systems and all that stuff, but it's paid off, it's running, it's working, and you can just keep on going. The public cloud for like OSC and AWS and Google, those get you going up almost immediately. You have to get your own system set up, but you no longer have to manage that hardware in-house, and you don't have to deal with fluctuating power and cooling requirements. And at this point, it's just project-related expenses. Whenever you need a boost to run, a couple hundred runs, you can just go right out, run those runs, and be done. And that can turn around runtime or time to solution from a couple of weeks on an internal system where you had limited capital to go out and buy a bunch of chips and cores, to suddenly you can spread out these runs over a couple thousand cores, and instead of a month to turn something around, maybe it takes a week. And that gets you out the door a whole lot faster for your final design. Then another option is that integrated cloud. And you no longer have to go out and set up your system on a cloud provider. It's already built into Star CCM Plus, and it's already ready to go. As soon as you've installed the software, you can basically in 2 clicks have a simulation up and running on a cloud. But once you have something up and running, there's the automation aspect of it. For OpenFOAM, we've worked with that for decades, and there's a lot of automation you can do around that, and we have done, and our customers have done as well, for Python scripting generally, to take a lot of that grunt work out of getting a model up and running. Without a lot of that automation, first OpenFOAM case could take several days to get running, just because you're editing dozens of text files and trying to get all that operating without a GUI to show you specifically what's going on. The next kind of model would be a Star CCM model, where you have a GUI, you can go through and build everything, and it has a nice function to where you can write Java macros. And unlike something like OpenFOAM, you can hit record macros and go through and record your whole workflow and streamline that. So once you've done a couple model builds and kind of tuned in your process, you can start just running a macro and building case after case, and that time to go from new geometry to final case shortens substantially. And all of that's just freeing up engineering time. And kind of the next step past that, once you've got an automated workflow for OpenFOAM or Star or anything else, is how do you go through and do optimization? And that's where a lot of this automation has to come in. There's tools like HEEDS, pictured down here in the bottom right, where you can import a bunch of different packages and go through multiple steps. So we'd use this recently for an optimization where we had to draw something in NX and then push it into Star, and then push it out of Star to do some other post-processing, and then get some tabulated results after that. Once you've kind of set up one of those workflows, you can go from, doing multiple designs a day in Star to suddenly taking HEEDS and doing DOE, design of experiments, or Latin hypercube optimization, or gradient reduction optimization, and start generating hundreds of runs in a matter of minutes. And then you get back to what's your HPC system you're running on, because now you have the ability to make a bunch of runs. But then for some people, there's no need to go through all of this, and they don't want to become CFD experts. They want to get results and they want to move on. And that's where something like these vertical apps come in. And that's where we like to provide some turnkey results for things like TS Auto or TS Truck, to where you don't have to go through and build your simulation and do all that upfront learning. All that has been done, and it's been templated, it's been validated, so that a user can go in, just upload a new rear wing for a car or a new side skirt for a semi truck, and run that and get results back. And for things like the truck app, that's been certified through CARB, so you can go through without even physical prototyping and end up with a a carb certification for a part. And that's kind of swinging from one end to the other on automation, to where you start and do your own automation, or you rely on automation that others have done for you. And then this kind of takes us to, how do you manage that data? Because once you get an HPC system, or how you want to run, and you get your workflow automated, that can end up generating a lot of data. And there's a tool out there, TS Results, that is sort of solver agnostic. So if you're working with OpenFOAM or StarCCM or Fun3D, you can read all that data in and collate all of it, so that, you know, 3 different engineers have 3 different styles of reporting. But with a tool like this, all of them see the same data the same way, and it's consistent across, you know, whole company. And you can either do something like this, to where you have automated report generation and databasing of all your results, so it's all in one place, or you have to start from scratch and start with your own in-house development and kind of define those standards and define how to collect all those results and kind of build that up. And it is involved, but it is something that is incredibly important, because as you build up all those automations, you free up the engineer's time massively to actually get into the design work, the analysis work, instead of just managing Excel sheet after Excel sheet. But some tools like HEADS and Design Manager inside StarCCM, they have some of that built in. If you go through and do a optimization or a Latin hypercube design of experiments, those will tend to already create nice, clean reports for you, but you don't have to automate all that data collection. But if you do multiple designs and multiple explorations, now you've got to manage hundreds of runs and batches and try to collect all that. So it is a balancing scheme to deal with all that. And then really, that's everything I have